Designing your power supply using energy harvesting technology has never been easier with Spansion's latest addition to their online tool, Easy Design Sim. At APEC 2014, Spansion and Transim demonstrated their energy harvesting PMICs. Here's the basic system. 2 transmitters, one with solar energy and one with piezoelectric energy, power remote sensing devices which circuitry includes a transmitter. Let's listen to Brian Thomas explain it at APEC 2014.
No power source, no batteries. And you notice no wires to it either, right? But what's this? I just sent a signal, but I don't have any power to this board. So what I'm looking at here is an energy harvester. And what this does is put enough energy into some capacitors where this nice PMIC from Spansion basically senses when there's just enough power to allow this microcontroller from Spansion to basically send a signal to the radio saying something happened to my sensor. Right? But the beauty of it is it has no batteries required, so this can sit out in the field and no one has to go deal with it ever because it's in a box, right? So another example is this guy. You can see the temperature sitting here. The last time was 318. It's a lot warmer in here today than it was yesterday. But what we have here, solar cell, same basic design, no battery, right? And so if I take and I put my finger on this one and let it warm up, there it goes. But it did that just because of the power on here. So, yeah. So what Spansion has done is they've created this very nice power management unit to do the microcontroller. But in order to do that, you have to design the circuit. And so what happens is we have a tool that Transim has developed that allows you to do this design. And at this point, we're going to work with the MD39C811, which is the part we're working with here. And I'm going to select it. So the first thing I got to do is select a harvester. Well, what I do is I come in here and I can select a whole range of harvesters. I can do some smart material, I can do a custom solar, but let's just stick with the solar because that's what I happen to have on this one. And oh geez, how much light do I have? Oh, I got 2,000 watts. And let's apply it. Now, in this design, I happen to know that I've already pre-configured it, so I don't really have to think about it. But at this point, I have a capacitor for the input. I have a capacitor on my output. The design has told me this is kind of what I need to do, but I can change these if I want to. But I'm going to go ahead and accept the defaults and apply it. And see, it's calculated that my harvester is going to give me 845 microwatts. So as long as I keep my average power draw below that one, I should be good. So I can come in here and set basically how many steps my microcontroller needs to do its function. It's got to go through an initialization. It's got to do some read-write activities, and we've assigned currents to those activities. But of course, I can always come in here and change the number of steps. I can put up to 20 steps in here, but for the sake of demonstration, I'm going to leave it at the defaults. I can come in here and name my steps so that I can see what each of these steps actually means. And I can actually change the profile that I see here. So we'll go ahead and apply this and see what happens. And what it does, it calculates, here's how much energy was stored, and here's how much time it took to get the input energy to a level that the microcontroller, that the PMIC can work with. And then in the initial pass, it took out that much energy, right? So it's definitely below that. And it basically went into standby for this long. So we know that there's no deficit in the energy balance. We do the same thing on the repeats, and we can see, hey, this is good. And in the time scale we looked at, it was able to do 6 cycles. So let's just look at those real quick. And you can see here, the PMIC, basically, it takes time for the input voltage to get high enough before the output voltage can come up. And at this point, when it's finally reached its good voltage, it says, I'm going to fire and send my signal out here, my temperature reading, and then I'm going to go into standby and wait. And so basically it charges back up, goes to the max, to the voltage, and sits there and waits for the next cycle to happen. And it just repeats. And as long as it's not gone below that minimum voltage line, this system should be good. If I say were to put this into a low light environment, I'm going to reduce my input energy, my light coming in, set that down. I'm going to keep everything the same here. But I have to run through the calculations to make sure that it gets to where it needs to go. And you can see here, it managed to get through 1 cycle, but there was not enough energy to let it charge right back up. And so it got 1 cycle, and that's what our results are saying. It did 1 signal, but it can only do it 1 time. Back to the normal waveform we had. Now I'm going to take my good design, and I want to look at what that looks like from a system level and what my actual waveforms look like. So at this point, I'm now designing the circuit around this PMIC to match what I just checked was going to be good. And so right now I have a model behind this one, and I'm able to run the simulation. So if I click run transient, what it's going to do is it's going to go through, use the model that Transim has developed for this part, and it'll show you all of the waveforms that we have here. It'll show you the power in, it'll show you the voltage in, it'll show you the V out, the I loads, everything else. But we have to wait a few minutes because it takes time to get there. So now I can go in here and I can look at my results. And you can see here it took some time for this to come up, charge up. I can zoom in here and look at what happens during my pulse. In this case, what we're doing is putting an average pulse into it to look at what the output voltage looks like. And you can see here it switches, and then it comes back and goes right back to the voltage. It's going to take some time for this to charge back up. You can see from here to here.
So the 2,000 lux that you had was for this?
Pardon?
The 2,000 lux
was for this case. Yeah. And you can see here my output voltage started at 3.63 volts, and at the end of that cycle it went to 3.615. It's because we've averaged that energy over a longer period of time. But I can go in and look at different waveforms here, standard waveform viewer for the tools. I can go in here, pick the bomb. All my components will be magically selected. I can even go to Arrow and see what the pricing and availability of them is. And if we just give it a second, it'll come in here and tell me what's available and what's not. Yes, and you notice I don't have a capacitor here. I'm going to go in and say, here's what I need. Let's make it a little bit bigger. There we go. So I got a capacitor. I can come in here, apply that capacitor, and it's not in stock, but it's not that expensive. And then, of course, I can go to my summary, and I have my design, all my components, my waveforms, my system, and my results that we looked at earlier. And that's the design simulator in a nutshell.
You're welcome.